Hello, fellow physics teachers! Mabuhay sa inyong lahat! Welcome to our program, Physics in Everyday Life. Are you ready for another half hour of learning by doing? In the previous episode, we left off with the question, are current carrying wires affected by an external magnetic field like that of a magnet? Today, we will try to answer this question. So join me in this episode on EM swings and motors. We have learned from the previous episode that current carrying wires behave like magnets because they too produce magnetic fields. However, unlike magnets, the field produced by current carrying wires can be switched on or off and can be varied. The nature of this relationship revealed further that when the current is reversed, the magnetic field points in the opposite direction. Stronger fields are produced by a coil of wire than by a single loop or a straight wire. The strength of an electromagnet can be increased by putting an iron core inside the coil, by increasing the current through the coil, or by increasing the number of loops of the wire. To learn more about the nature of electromagnetism, let us explore the effects of an external magnetic field on a current carrying wire. Let us start by looking at examples of toys, kitchen gadgets, and other machines around us. The things you see on screen have one thing in common. All of them operate with motors that convert electrical energy to mechanical energy. Motors can either make things rotate or move objects along a straight line. They range from small ones, as in toys, drills, vacuum cleaners, and electric fans, to larger ones like those in washing machines, to very large ones, as in heavy machinery. The invention of electric motors helped improve man's daily life. Human activities can be accomplished at a faster rate and with greater efficiency by using electric motors. Therefore, life became more comfortable and convenient for modern man. Now, what is the principle behind motors? This is what we will discover today, dear teachers. But before we continue, let's have a short break. Don't go away. Welcome back to our program. Let us begin by observing the effect of an external magnetic field on a current carrying straight wire. To make this activity more exciting, we mounted a straight wire like this in a swing. We're going to call this the electromagnetic swing or the EM swing. In this setup, you can see a piece of straight wire here that has been fixed between the poles of a strong magnet. If current passes through the wire, what do you think will happen? Okay, so let's see what will happen. We turn on the power supply and watch closely. So here goes. The wire is pushed away from the magnet. Did you see that? This movement or deflection of the wire in the presence of the magnet is called motor effect. What brings about this motor effect? In our activity, we were able to see that there is a net force acting on the current carrying wire in the presence of an external magnetic field. This force is called the magnetic force. The motor effect happens because of the interaction between two magnetic fields, one from the magnet and the other one from the wire. As you can see, the field between the poles of the magnet is nearly uniform. We learned from the last episode, if you remember, that the current through a current-carrying straight wire produces a circular magnetic field. This circular field produced by current squashes the field between the poles of the magnet. In effect, moving charges in the wire experience a force perpendicular to the external field. The wire is tugged along with the moving charges, hence the wire is deflected. Fellow teachers, in this simple activity on the motor effect, there are three quantities found to be related. These are the current I, the external magnetic field B, and the magnetic force F. How they are related will be demonstrated in our next activity. In this setup, the direction of the electron current in the wire is from the negative to the positive, so in that direction, while that of the magnetic field is downwards, from the north to the south. Now, if the switch is momentarily closed, what happens? All right, so let's watch it. There it goes. The wire is deflected away from the magnet. We shall now represent the quantities using vectors, and we have our model here. So the current is to the right, represented by this vector. The magnetic field is downwards, represented by this vector. And the magnetic force is forward or out of the magnet, that is represented by this vector. This model illustrates the relative directions of the current, the magnetic field, and the magnetic force. We will continue with more interesting activities after this short break. Don't go away. Hello, fellow teachers. We're back with more trade secrets for you. Do you know that there is an easier way to predict the direction in which the wire will move in an external magnetic field? This is what we call the left-hand slap rule. Let's try it together. Your thumb represents the direction of the electric current. Your four fingers will represent the direction of the magnetic field, while your palm will represent direction. In this setup, for instance, the current is to your right, so your thumb must point to the right. Magnetic field is downwards in this direction, so your four fingers must point downwards. Where does your palm face? It faces in this direction, which means that the force is in this direction or away from the magnet. Do you agree? All right, so let's find out. Let's go back to our setup here, and we switch on the power supply. All right, look again. See, our prediction about the force direction is correct. Suppose now we change the direction of the current by changing the polarity or the connection. All right? Can you predict which way the wire will move? Let's try it. Okay, observe now. Did you see that? The wire moved towards the opposite direction. It moved towards the magnet. Hence, we could say that magnetic force is in the opposite direction when the current is reversed. Today, you were able to learn about the relationship among directions of current, magnetic field, and magnetic force. How about the magnitude of the magnetic force? What factors would affect magnetic force? Watch carefully the effect of changing some parts of our original setup. We have here our colleague and scriptwriter, Dr. Aurora Mendoza, who will assist us in our demonstrations. If we use a weaker magnet, what would happen? All right, Al, switch on 1. 3, 2, 1. All right, the swing moved through a smaller distance away from the magnet. Okay, now, if we add another identical magnet, that will mean that we will be exposing a longer length of your conducting wire in your external magnetic field. Okay, Al, are we ready? All right, switch on 1. 3, 2, 1. The swing moved farther away from the magnets. Then we increase the current. Our original setup has 2 amperes, while the other one will have 4 amperes. So switch on 1 again, Al. Ready? 3, 2, 1. In effect, the swing also moved farther away from the magnet. We can therefore say that there are 3 factors that affect magnetic force: magnetic field strength B, length of wire exposed to the magnetic field, L, and the current I. So we would like to thank Al for the assistance in our demonstrations. Thank you very much. The magnetic force is related to these factors in the following equation. F is equal to B I L. Magnetic force is equal to the product of the magnetic field strength, the length of the wire exposed to the field, and the current. We have seen the effect of an external magnetic field on a straight conductor. Suppose the conductor is a coil. Would the effect be the same? We will find out after these reminders. We promised to find out the effect of an external magnetic field on a current-carrying coil, didn't we? Well, here it is. We have here a coil of wire mounted on stationary contacts here. Current is passed through the coil by connecting the contacts to a power supply, or you can use a battery. A permanent magnet is used to produce an external magnetic field. What happens when the current-carrying coil is placed in an external magnetic field? Okay, let's try that. We will turn on the power supply. All right, are you ready? There, you can see that the coil rotates. In effect, this assembly of a magnet, a coil of wire, battery, and stationary contacts make up what is called a motor, a simple DC motor. The stationary contacts to the battery and the moving wires in the coil are always part of one complete electric circuit. How does a simple DC motor operate? Let us examine the motor here. When current passes through the coil, it flows in opposite directions. This means that if charge flows into one end of the coil, it must flow out from the other end. When the coil is in horizontal position like this, current from the two sides of the coil are in opposite directions. The forces acting on the two sides are also in opposite directions. If one side is forced upward, the other is forced downward. The coil rotates until it has turned to a vertical position like this. At this vertical position, the side which is going up can no longer go up, and the side which is going down can no longer go down. At this point, the coil has turned half revolution. The stationary contacts reverse the current direction in both sides of the coil. Due to this change in current direction, the direction in which the forces act also changes. Going up is now forced downwards, okay? And the side that was going down is forced upwards. This reversal process is repeated every half revolution so that the coil continues to rotate as long as current is supplied. So far, we have described only a very simple DC motor here. In larger motors, whether AC or DC, electromagnets energized by a power source are used instead of permanent magnets. Electromagnets can produce very strong magnetic fields, so that more powerful motors can be built than is possible with permanent magnets. In this case, instead of a single coil, many loops are wound about an iron cylinder. This is called an armature. The armature rotates when energized with electric current, such as this one used in electric fans. Now, let us summarize the concepts and principles of electromagnetism that we learned today. Current-carrying conductors are deflected in the presence of an external magnetic field. This deflection is called the motor effect. The motor is because of the interaction between the magnetic field produced by current in the conductor and the external magnetic field. The net force that acts on current-carrying conductors is called magnetic force. Magnetic force is equal to the product of the magnetic field, the current, and the length of the wire exposed to the magnetic field. A current-carrying coil rotates in an external magnetic field. The principle behind motors is that moving charges experience a force that is perpendicular to their motion and to the magnetic field they traverse. Before we end, let me pose a question. If current produces a magnetic field, will a magnetic field also produce a current? How? These are some of the questions that we will try to answer in our next episode. Again, we hope you enjoyed and learned a lot from our fantastic but inexpensive demonstration today. Till then, this is your host, Dr. Zeni Domingo, greeting you. Good day.